Hello, my name is Feven Markos Hunde. I am PhD student at Center for Theoretical Physics in Warsaw, Poland. Today I will talk about the effects of cosmic wave on dark matter Subhalo properties. So this work is in collaboration with many people from CT, PAS here in Warsaw, and also from East. To give just some recap about lambda seeding paradigm, it predicts that small density perturbations grow because of gravitational instability and the results form bigger structures like viralized dark matter halos. It also predicts that dark matter halos form hierarchically, that means small structure, low mass halos collapse earlier and merge to form the larger systems over time. It also predicts that galaxies are embedded in massive halos. So with like these substructures which are merged inside the large halos, that means it assumes that these substructures inside the halos also host different galaxies like satellite galaxies. It also assumes that dark matter halos, like galaxies, also form hierarchically. That means low mass halos or satellites galaxies form first, then they collapse with time and merge together to form the bigger or the larger systems. It predicts also galaxies are embedded in massive halos, so they are living there, and also that substructures inside halos can host satellite galaxies. These substructures are called subhalos. As you can see here, like in our sketch, there is like a bigger yellow boundary. It's like imaginary boundary of one viralized halos in the yellow small like circus represents substructures inside that halo. When we come to cosmic wave, it's like a large scale structure. It's a home for galaxies and halos. Morphologically, it considers four elements. The elongated structures, which we see are filaments, and the other are the overdense regions, and we see like more brightest regions in this like simulation results are called nodes or nodes. There are also sheet-like structures which surround this words in the like the other one is like the under-dense region, but which consists the largest volume of the cosmic wave is assumed to be void. So galaxies and dark matter is used as a tracers of cosmic wave. So we can see from like simulation here, from illustration, also from like galaxy survey of stasis, this wave-like filamentary structure. So if like dark matter halos in galaxies live inside these like different cosmic wave environments, how these environments affect the properties in their distribution. So there are a lot of previous works which were done on the environmental effects on dark matter halos also in galaxies for to check like to see one of them is like how halo mass function is dependent on environmental dependence. So halo mass function is the number density of halos in each specific environment. As you can see, like the many works have like previously shown that dark matter halos and galaxy properties and their distribution are affected by their location in the cosmic wave. So, for example, if we see the halo mass function, it shows like the number density of halos in that specific environment. We can see like how cosmic wave environments affect us. Like, for example, for the massive halos, mostly they are dominated by nodes or clusters. But when we come to like 10 to 13 or 10 to 12, like Milky Way mass range, now we have like filaments dominate the number density. But, but for like the low mass range, less than like 10 to 12, we can see like the halomas are uniformly distributed for filaments, whorls, and voids except for clusters. So that's our main interesting region for this study. So if the halos are evenly distributed among filaments, whorls, and voids in this like less than 10 to 12 region, that means more of like less than the Milky Way sized halos, how like their substructures inside these halos are affected by the environments of their hosts. So why do these substructures or subhalos matter? When we talk about dark matter subhalos, we are talking also about the associated satellite galaxies hosted by these subhalos. So where we find out how these cosmic wave environments affect the subhalos properties in their distribution. It will help us to understand the satellite. The other thing is subhalos also matter for the cosmology. So abundance of subhalos is cosmology dependent. If it and it also will give us a constraints on power spectrum on small scales. The other thing is the dynamics. Subhalos are associated with different dynamical processes like tidal stripping, tidal heating, or dynamical friction. So after they merge to their parent halos, they will be affected by different these dynamical processes. So when we are studying about the cosmic wave environmental impact on these subhalo properties, we are also trying to figure out in which environments these subhalos are more affected. So our main goal is to study the abundance of dark matter subhalos in the properties within different cosmic wave environments. Also to investigate the dependence of these subhalo properties on their host halo mass and other properties. So for this work, we use Copernicus complexo simulation. So it's dark matter only domain simulation, and it has different boxes. The parent box is the size of our 170.4 gigaparsec H inverse, and we have also the medium and high resolution suits inside this one. But for this specific work, we use the parent box, and it consists around 1,620 cube dark matter particles, in each particle assumed to have a mass of 6 times 10 to 6 mass. And also the simulation has both cold dark matter and wild dark matter flavors, and the initial cosmology parameter is WMAP, based on WMAP 7. So for this specific work, we use only cold dark matter flavor. So for structure identification, to identify the halos and subhalos, we use subfind algorithms. It's based on like over densities. So first it identifies the FOF group and within a distance of interparticle separation of zero point 0.2. Then inside that if each FOF group it tries to identify the substructures using local over density. Also subfind calculate some of the subhalos and halo properties. For cosmic wave segmentation, we used Cactus. It's like adapted version of Nexus algorithm because it uses different input as different field has an input and gives us cosmic wave environments. For this specific work, we used density fields as input and will identify the different cosmic wave environments based on eigenvalue conditions. So it's the like we are have it calculates the Hessian matrix, and from the Hessian matrix it calculates the eigenvalues of the density field. So it's like if the three if we have three eigenvalues, and if three of the eigenvalues are less than zero, it's assumed that like specific region as nodes or nodes, and if two of these eigenvalues are less than zero, it assumes that region as filaments. And if one of the eigenvalues is less than zero, it assumes that region as walls, and the other regions which are not classified to any of these regions are assumed as voids. The other like advantage of Cactus also makes us is multi-scale detection because this process is repeated to different scales, and we take the maximized result from each of the signatures for a specific grid point. So it's more of like scale independent identification method. The first property we have studied is Subhalo mass function, and its dependence on different environments. So this is to quantify the abundance of subhalos in different environments. First, we categorized our host halos by mass. So we have like three mass means from 10 to 12 to 10 to 10. And like we use M200. M200 is a mass within a radius of R200. R200 is a radius at which the density of the halo is 200 times the critical density. So when we see like in 10 to 12, now we have only subhalos hosted by halos in walls and filaments. And then as we can see from our plot, the number of subhalos are higher in halos hosted by filaments in this mass way. Also, when we compare with the equally weighted sample, we introduce a new sample. It's called equally weighted sample for our study. It's because when we compare like the each environment subhalo mass function with the all volume sample, it may be biased because the all volume sample is more like dominated by the environment which hosts a large number of halos. So we select equal number of host halos from each environment, and we compare the subhalo mass function from each environment to the equal weight sample. So when we see the relative difference with the equally weighted sample in the like in lower panel, we can see like the large number of the difference is like higher in a high mass int of our mass function. Also, for we fit our like mass function using exponential power law fitting. In the previous works, it has already been shown that power law is a best fit for subhalo mass function, but it doesn't fit well the high mass int of like our mass function. So we use exponential power law fitting. As you can see, the solid line represent that. So from our exponential power law fitting, the normalization and the power law exponent shows weak dependence on the environments in the host halos, but the expo, exponential term depends strongly on the cosmical environmental locations. Also on the host halo masses. When we go to the like low mass range, now we can see how the environmental effect is more clearly seen when the mass of the hosts decrease. So from 10 to 12 to 10 to 11, still the number of subhalos hosted by halos in filaments are higher than the other environments, but the environmental dependence in the difference is more clearly seen in the lower mass base. So from our subhalo mass function, we can see that the environments of different cosmic wave environments affect the subhalos hosted by halos in there, living there, and also the exponential power law fitting depends also like on the environment values depends on the environment's locations. We can see like the subhalo richness because mostly the high mass in is affected by the environment. We can see like the subhalo richness for like our normalized subhalo mass greater than 0.04. So we can see like the large number of subhalos in filaments, then in walls, in like in voids. Also, this is like different in different host halo masses. The other property is subhalo velocity function. It has more of similar similar property like subhalo mass function. It also used to quantify the number of subhalos or the abundance of subhalos in different environments, but subhalo velocity function is more of a stable method to quantify the number of subhalos because it's not that much affected by strong tidal processing of subhalos and the boundary definition of subhalos. The other thing is also strongly related with observable properties than subhalo mass. Still, when we see the velocity functions of our subhalos, it shows more of like a similar pattern that its dependence with like environment increases with the decrease of host halos and the number of subhalos in filaments are higher than the ones in walls and voids, and the voids are the least ones. In the other property we have studied about subhalo properties dependent on the environment is the Vmax Rmax relation. Mostly to quantify the density profile of halos, we use NFW profile or NSTOP profile, but we can't use that for subhalos because they have like more of a truncated internal density profiles because after they merge to their parent halos, they are affected by different dynamical processes. So the Vmax relation will be the best one to quantify the characteristic density of subhalos. Vmax is the maximum circular velocity of subhalos, and the Rmax is the radius at which this Vmax is attained. So when we see for like the same Hostello mass beams, our Rmax in 10 to 12, like for a fixed Vmax values, the subhalos Rmax values like higher for subhalos inwards than the filaments. That means on average they are less concentrated than the ones in filaments. But when we go to the low mass range, the Rmax values are like higher for the ones in voids than the others. So that means on average, like the ones in voids are less concentrated. And also when we see like to our low mass range, the environmental impact in the Vmax Rmax relation is also increasing with decreasing of our host halos, and also like that means that their concentration is more affected like by their environments when their host halo mass decrease. And it also shows that the concentration is also affected by the host halo mass. So the other thing we can like see from this Pmax or max relation center or the concentration of subhalos is if we lower the mass of the Milky Way halos, it can lower the central densities of subhalos. This we can like alleviate the too big to fail problem. So to summarize my presentation, both the subhalo mass function and velocity function shows that higher subhalo count is found in halos which are hosted by filaments and the lowest one in voids. Both like functions shows that the cosmic wave is more effect is more pronounced in the lower parenthetical mass ranges. And the other thing is the exponential power law fitting works well for like subhalos mass function than the single power law fitting, especially for the high mass in cat. And the Vmax Rmax relation shows that subhalos hosted by halos located in filaments exhibit on average more concentrated density profiles than the ones in modes and voids, and the ones in voids are the least concentrated one. So from our result, we can conclude that the cosmic wave and the host halo mass impact both the subhalo abundance and the other properties of subhalos. So these can influence the potential satellite galaxy properties and their distribution in the universe. Thank you.